Okay, welcome to class 12 of Physics 350. This is our first class on magnetic forces. Um, it will not be covered on the first exam, but we'll begin to explore it here to give ourselves a little break and a chance to review a little bit in the final class before uh, the test on electrical forces. This is section chapter 5.1 of the textbook, and we're going to review a bit about the magnetic force and also look at a couple of one especially interesting application of electrical forces and magnetic forces together. So the magnetic force is called the Lorentz force, and generally it gives rise, if we just have a magnetic field and a charged particle, to cyclotron motion. So the magnetic field on a charge q moving with velocity v and a magnetic field b is given by this cross product. The charge q, it's proportional to the charge q, it's proportional to the speed that the charge is moving, and it's proportional to the magnetic field, and it's at right angles to both the direction of motion and the magnetic field, as we'll see in a second when we look at cyclotron motion. And this is called the Lorentz force. If we have both electric and magnetic fields, the net force on Q would just be Q. We know that the electrical force is Q times E, so it'd be QE plus V cross B. So this is the most general expression for force when we have electric and magnetic fields. Okay, so what do charged particles do when they encounter magnetic fields? They generally move in circles, okay? And that's called, the technical name for that is cyclotron motion. A charged particle in the magnetic field moves in a circular fashion with the magnetic force providing the centripetal acceleration. So if we take a look at this charged particle here, this would be a positively charged particle. It's moving at the moment straight upward. The magnetic field is pointing into the screen in the minus z direction. And using the right-hand rule, which is a little bit difficult for me to illustrate here, but with v straight upward and b backward, the force is going to point to the left on a positive particle. And so if we have a particle moving upward and then it experiences a leftward force, that's going to curve it around, and eventually the particle will curve into a circle, like so. For example, when the particle gets to the top here, its velocity will be to the left, but the force will be down to the downwards toward the origin. So it's gonna have a centripetal force and a centripetal acceleration. So we get circular motion or cyclotron motion. And the magnetic force, if we set up the magnetic force equation, we get, since all three of these, since V and B are perpendicular, the magnitude of V cross B is just the magnitude of V times the magnitude of B. So we have QBV, QVB is equal to the mass times the centripetal acceleration V squared over R. And sometimes this is re-expressed by, let's see, multiplying through by R and then dividing through by V. That puts an MV on the right-hand side, and you recognize MV is equal to the momentum. So we just get the momentum is equal to Q times B times R. So if we send a particle through the bigger the charge, the bigger the field, the bigger the radius, the bigger the momentum of the particle must be. Okay, this leads to an interesting experimental technique for finding the momentum of a particle whose charge we know. For example, a hydrogen ion or a helium ion, also known as an alpha particle. Often we know the charges on particles. If we send it through a region of known magnetic field, so we know B, and we set that up with a magnet, and we know Q, then if we measure the radius of curvature of its trajectory, that immediately tells us the momentum of the particle through this relationship, because the particle will be going in a circle. We can measure the radius and we get the momentum. And if we happen to know the mass of the particle, we can get the velocity. Interestingly, if the particle here, the particle starts off with a velocity which is perpendicular to the magnetic field, so it starts out in the y direction, and where the magnetic field is in the minus z direction. If there's a component of the velocity parallel to b, so for example, if there was a small component of b along the magnetic field here, then according to the cross product, it turns out that component of magnetic field, that component of velocity, is not affected by the magnetic force. So it will just continue on unaffected, and we get helical motion. So we basically get from the part of the velocity which is perpendicular to the magnetic field, we get circular motion. And if there's a part which is parallel to the magnetic field, that part remains constant, and we just get a bunch of circles stacked on top of each other. Okay? All right, so we have the magnetic Lorentz force. We have the typical circular motion, and then we have helical motion if the particle has a velocity component parallel to the field. Okay, I thought it would just be fun to look at a mix of electric and magnetic forces on a particle. This was actually new to me. I hadn't, which there are lots of things new to me, but I hadn't seen this before, and it's called cycloid motion as opposed to cyclotron motion. So suppose we have a particle which starts off at the origin, and we put an electric field in the upward direction, plus z, and a magnetic field in the plus x direction. Okay, so what path will it follow? Okay, well, we're going to analyze in some detail this situation because it's kind of interesting, and it leads to some interesting aspects of differential equations. But let's just think a little bit first about what will happen physically. So initially the particle, let's suppose the particle is not moving. So without motion, the magnetic force would be 0 since it has velocity in it. So if it's a positive particle, it'll start moving straight up. And as it moves straight up, it will then encounter as it gains velocity, it will encounter a magnetic force, in this case to the right. If it's let's see, just a second here. Yeah, if it's a positive particle, it would encounter a force to the right, and it would start to curve in a circle. But notice that as it's curving, it's not quite a circle because we've got the electric field, which is acting on it as well. So it's not a purely circular motion. And when it comes back around to the other end of the circle, the electric field will act on it to slow it down very strongly. So it'll stop and slow down at this point. and then it will start that motion over again. Okay, so it's called a cycloid motion because it looks kind of like a point on the rim of a bicycle wheel might look like. Okay, so this is cycloid motion. All right, so let's see if we can analyze this. There's initially no force in the x direction, since there's no velocity, and the magnetic field only exerts force when there's velocity. We set the position of the particle at time t then as 0 in the x direction, and then y and z, and the velocity would then just be 0 and y dot and z dot. We can find the magnetic force at a given time as, or part of the magnetic force, the V cross B part, as by taking the cross product. So we'd have set up the cross product, x, y, z, and we have V just has y and z components, because there's never going to be any force in the x direction here, and z is in the positive, B is in the positive x direction. So if you work out this cross product, it turns out to be, if you look at the y term, 0, y hat times b z dot, okay, and that turns out to be a positive because there's a negative of a negative there when you work out the determinant, minus the other term is minus b y hat z, b y dot z hat. Okay, so that's V cross B. It's proportional to B, and it involves the speeds in the x and the y directions. Okay, how do we figure out motion? We apply Newton's second law. So we have the full equation, which is F equals charge Q times E plus V cross B. So we have Q times E z hat, since E is in the z direction, plus B plus our, since we have our Q out here, plus this is our V cross B that we just calculated up here. Okay, so this is the full equation. F would be equal to Q E z hat plus this expression here. And that's equal to, F is equal to MA, and A here, we can exclude the x direction because we know there's no motion in the x direction. So it's just going to be M times the, we're in Cartesian coordinates, so y double dot y hat plus z double dot z hat. Okay, so we can divide this into separate components. That is y hats and z hats. So in the y hat direction, we just have q b z hat is equal to m y hat, and in the x direction, the z direction, we have qe minus qb y hat is equal to m z double dot. Okay. All right. So it's definitely not wasn't obvious to me as I went through this for the first time what kind of motion this is going to produce, except that it's going to be a motion that combines at y and z motion, because both equations have derivatives of y and z in them. So how can we handle this? How can we solve this and get insight into it? So we can define what's called the cyclotron frequency. It's QB over M, and that turns out to be the frequency that a particle moves in a circle. A particle of mass M moves in a circle if it goes through a magnetic field of magnitude B, and it has charge Q. Okay, so that's the cyclotron frequency. But anyway, we can just define omega as QB over M. That just cleans things up a little bit. So this, we divide through here and we get y double dot is equal to QB over M Z dot, or omega Z dot. And here we have, oops, Z double dot is equal to QB over M minus QB over M Y dot minus QE over M minus QE over M. So we have to multiply QB over M by E over B to get QE over M. Okay, so you might want to just look at this equation here and this equation here and verify that they are the same equation with this definition. Okay, so we have two, what do we have here? We have two, remember these are ordinary differential equations because there's only one variable, which is the time, but they're coupled together. The second derivative of y depends on z, and the second derivative of z depends on y. Okay, so in class, we will go over how to, we'll do an exercise on how we can make sense of a differential equation like this. But the general solution, it looks kind of like sines and cosines, which makes sense because we have y double dots and z dots. So this looks like the derivative of a cosine would be a sine and so forth. But we have extra terms because of this e over b here. And we have constant terms. Just as a little hint, what we'll be doing in class, if we differentiate the first equation, we get y triple hat is equal to omega z double dot, and then we can solve for z double dot and equate that to the second equation, to the right-hand side of the second equation. And so we can isolate y triple hat and y hat, solve for y hat, and then go from there. But we'll do that in class. Okay, so we accept that those are the equations. Sorry, we accept that these are the equations for now, and still don't make a whole lot of sense mathematically, to me, at least. But let's assume that the particle started from rest, so that its velocity in the y and z direction is 0. And let's suppose that it starts from the origin. Okay, so it starts at y and z are at 0, and x is 0. X doesn't change, but we can just assume it's 0. Okay, so we have our two equations here. And then these, remember, for differential equations like these are called boundary conditions, or in this case, initial conditions, because they're the value of the velocity and the position at the initial time. In general, boundary conditions is the general term, but initial conditions here. So we have 4 boundary conditions, or 4 initial conditions, and we have 4 undetermined constants, C1, C2, C3, and C4. So that should be enough to get us a solution of these two equations. Okay, so these conditions determine the constants C1, C2, C3, and C4. Okay, and if we go through that, and we will go through that in class, okay, we'll see, well, at least some part of it you guys will do, and then I'll show you how the rest is done. We find that y is equal to e over bt, which we can write as e over omega b omega t, minus E over omega b times sine omega t. So that means that C2 has turned out to be minus E over omega b, this constant C2. And you can see that here because here's for z of t, we have C2 is E over omega b minus E over omega b cosine omega t, and C4 turns out to be E over omega b. Okay, so so here are two equations. These are the trajectories of y of t and z of t, but what does it actually look like? Well, we can use a nice little trick to simplify. We can let this constant, which is out in front now, E over omega b, which, by the way, has, if you work it out, has units of distance, and let r equal to that, and then solve for sine of omega t in the first equation and cosine of omega t in the second equation, and then use the fact that sine squared plus cosine squared is equal to 1, the trig identity. Okay, so if we do that, so for just quickly, for example, if we take the first equation and we write this as y of t is r omega t minus r sine omega t, right? Because this we've called r, and then solve for sine omega t, we get y minus r omega t is equal to minus r sine omega t. And if we do something similar for cosine omega t, we get something times, we get r times cosine omega t. Then we square both and add them, and then the sine squared omega t and the cosine squared omega t become 1. And we get this equation here. This starts to look like something that we can make sense of, because it's something involving y squared plus something involving z squared is equal to r squared. And you may remember that the equation of a circle, the equation of a circle of a unit circle is, for example, y squared plus z squared equal 1. And if you subtract off a value, that just shifts the origin of the circle. Oops. So this is the formula for a circle of radius r, where r is defined by these constants here. And the center would be at x equals 0, because x never deviates from 0. Y is r omega t, and z is r. Okay, so z is equal to r. So we interpret that. We can interpret that as something which travels. Its y component of the center of the circle travels as r omega times t. So r omega would be the velocity. So the center travels in the y direction at constant speed omega times r, which, if we come back here, omega times r is equal to E over b. Okay, just an interesting fact there. And the center actually has position r, E over omega b. So even though it looks like it's centered on z equals 0 here, it's actually centered on z equals E over omega b. And so we get this cycloid type motion. Okay, so that's just our initial introduction into magnetism. We looked at the Lorentz force equation, Q V cross B. We looked at circular motion that happens when there's, or helical motion, which happens when there's just a magnetic field. and we looked at this interesting cycloid motion, which happens when we combine an electric and magnetic field. And it's going to help us understand a little bit more about differential equations as we do a couple exercises in class. Okay, great. And just once again, this material is part of the next section, is not covered on the upcoming test. Thanks, and see you in class on Tuesday.